Hello, everyone, and welcome to our first quarantine lesson special. So we're going to dive into 6.3, which is, which would have been the first lesson that we would have done after spring break if it wasn't for what's happening in the world right now. So yeah, let's just dive into it and we'll see how it goes. So 6.3 is all about modeling data using the polynomial functions that we took a look at. So if you'll remember, we spent a little bit of time in the previous lessons of this unit first talking about constant graphs that are horizontal, linear graphs. Both of these we would have seen in grade 9 and grade 10. We spent some time reviewing quadratic functions, which we would have saw last year in grade 11. And then the better part of the last day was cubic functions. So you guys should be pretty familiar with the kind of shapes we would expect out of a graph like that. So 6.3, what it's all about, what this lesson is all about, is regression. So you should remember regression from the last unit when we were doing logarithmic functions and exponential functions. But for this unit, we're going to stick exclusively with the polynomial functions that we have here. Okay. So for the most part, we're going to be using Desmos to perform all these regressions, similar to what we did in the last unit. Okay, but the trick now is, now that we have these four polynomial functions at our disposal that we're familiar with, it's up to us now to decide which of these shapes, which of these patterns are going to best fit the data that we're given for any particular question that we have. We can't put our data in to Desmos and have Desmos tell us which one is the best to use. Desmos is not capable of doing that. I'm sure there's some other software, some other more powerful software that's out there that would be able to do that, but Desmos can't. So it's up to us to determine, given a set of data, which model, which function, which pattern, which line that we want to use. We're familiar with the shapes at this point, so that's something we should reasonably be able to do. I'm going to talk a little bit more about which data fits best later. The last example that we're going to do today deals with that, but let's not worry about that for now. Let's get into the first example. Let's get into the first question, and I can kind of show you exactly what it is that you'll be expected to do today or after today. Okay, so this example is straight from your book, and it deals with the concentration of a medication in a patient's blood. Okay, so the concentration in milligrams per liter of medication in a patient's blood is measured as time passes, so measured as a function of time. Susan has collected the following data and is attempting to express the concentration as a polynomial function of time. So polynomial, what that means is we are not using logarithmic or exponential functions here. Neither of those are considered to be polynomial. The only four polynomial functions we know at the moment are these ones, so constant, linear, quadratic, and cubic. If you remember, polynomial functions are made up of terms separated by addition or subtraction that have whole number coefficients. Okay, so basically what we're saying is if we're using polynomial, we're going to be using one of these four available to us. Of course, there's more polynomial functions that exist, but for this course, we're only going to be worried about these four that we've seen already. Okay, So we have two variables here. We have time, which of course we're going to be placing on our x-axis, and we have concentration of the medication, which we're going to be putting on the y-axis. So the first question here is to plot the data on the grid to investigate the type of relationship between concentration and time. All right, so concentration, we're going to be putting on the y-axis. That's in milligrams per liter. And we're going to be putting time here on the x-axis in hours. So I'm just going to be making a rough sketch here. I'm not going to be super accurate. We just want to get a general feel for what the data is going to look like when we put it on a graph. What shape is it going to take? Okay. So if I take a look at my x values up here in the table, it goes from 0 to 9. So if my 0 is down here, it goes up to 9, and about halfway between 0 and 9, or exactly halfway between 0 and 9 is 4.5. So I'll leave that as my graph for now. My y-axis goes from 0, and it looks like the highest value is 47.8. So I'll put that up there. Okay, that's where it caps out. So now we need to take a look at the data. So if we notice, when we start at time 0, the concentration is 0. Makes sense. The patient didn't take any medication at time 0, so the concentration of medication in their blood should be 0. So from here to here, we notice that the concentration is increasing, and then after that, the concentration begins to decrease. All right. So I'll look for the highest points. It seems to be at this point right here. That's our highest point, 4.5 and 47.8. So that's going to be right about here. So that is 4.5 comma 47.8. So what that tells us is 4.5 hours after taking the medication, the concentration in the patient's blood is 47.8 milligrams per liter. We also have the 0.00, which of course is down here. So just to make a rough sketch, of course we're increasing, then it starts to level off a little bit, it seems, at the start. So it goes up here. And after there, it drops after 9 hours to about 20.3. So taking a look at my scale on my y-axis, 9 hours obviously is here, and then 20.3, let's say approximately here, for example. So maybe the graph is going to look a little something like that. And of course, this point represents 20.3. Okay, so that's a rough sketch. Again, not super accurate, but that's fine. So based on the shape that we have here, we need to go back and take a look at the polynomial graphs that we're familiar with. All right, so we'll go and take a look at these. So constant graph, linear graphs, of course, you should remember linear graphs can slope down. They could have a steeper slope. They could have a shallower slope, right? Quadratics, we know quadratics could be very skinny. We know quadratics could be quite fat, right? We know quadratics could open down, right? Cubics, remember from last day, so this one has two turning points here and here. So a turning point is when the graph goes from increasing to decreasing, or from decreasing to increasing. So this graph has two turning points. It could also have two turning points going the other way, right? It could look like that. You should also remember cubic functions, it's possible for them to have no turning point, and instead to have a point of inflection. That's where the curvature changes. So the graph could look something like that, where the graph is still always increasing, but the curvature right here would change. That's a point of inflection, and of course it could go the other way as well. So those are the 4 shapes of cubic functions that you should recall from our last section here in this chapter. Okay, so based on those 4 shapes, we need to make a decision as to exactly which one is the case for our question. I hope you agree with me that this is neither cubic, nor is it linear or constant. It is in fact a quadratic function that is opening downwards, because it has a 1 turning point, which is the maximum there at 4.5 and 47.8. So you should remember quadratic functions, they will always have 1 turning point, a maximum if it opens down, and a minimum if it opens upwards. Okay, so we know this is going to be a cubic relationship here. Or sorry, a quadratic. All right, so next question. I don't know why it's question A, when A, B, A, whatever. On a graphing calculator, enter the data into lists, time in list 1 and concentration in list 2. Create a scatter plot of the data and use the quadratic regression feature to determine the polynomial function, blah, 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 that best fits the data. Round the parameters A, B, and C to 2 decimal places. Okay, so we don't really need to use this at all. This information here is for a graphing calculator, an old school graphing calculator, something like a TI-83. But for this class, of course, we've been using Desmos. So Desmos is what I'm going to be using here. Here, I'll bring up new Desmos. This is from before. Actually, we'll take a look at that that graph I just had up there in the next question, but we're going to start fresh for this one here. Okay, so just going to make sure I'm still recording. I am. Good. So what we're going to do is we're going to enter the data that we had from our first question into Desmos. So we're going to go here. We're going to add an item, hit the little plus sign, and then we're going to make a table. Okay, and we are going to enter the data that we have from our table. So our first piece of information from the x coordinate, or from the x value, was 0 for the time. Then it went to 1.5, and then here you'll see that Desmos pre-fills the rest of them, assuming the rate is the same. So if you'll notice, of course, we're going up by 1.5 each time in the question. So that's what Desmos is assuming you're doing here. So it will do that for you all the way up to 9. And then the y value is the concentration that we need to enter manually. There's no real pattern to that one. So at time 0, we had a concentration of 0. After 1.5 hours, we had a concentration of 26.9 milligrams per liter. After 3 hours, we had 41.2. Then we had 47.8 at the cap. It went down to 46, and then 36.8. And then finally 20.3. All right, so there's our data there. You can hold your mouse button on the green circle there to bring up this menu. I use blue in the notes, so I'll change the color to blue here. And if you go down, you can see the little magnifying glass. That is the zoom fit feature on Desmos. I'd go ahead and click that so the graph zooms out to best show you the points that we've put together for this table. If you want to, you can go in, bring it up again, and you can add the lines feature. If you want to, if it helps you visualize it. As you can see, these are all straight lines. When you use this function, Desmos does not add a curve, which is not representative of the true data that we most likely have. It's pretty rare that you would get a pattern with only straight lines like this. For that reason, I'm going to keep mine off, but if it helps you, if you like it, you can keep the lines on. It doesn't really matter. Okay, so given our data here, we now want to create our regression line. We want to tell Desmos to do its best job at suggesting to us a function that best represents this data. Okay, so if you remember, the general form of a quadratic equation is going to be y equals some value a times x to the power of 2 plus some value b times x plus some value c. So you can see here that Desmos hasn't done anything. It hasn't given us our line. That's because we need to do a few special things. So if you take a look at our table here, we're not working in x and y, we are working in x1 and y1. So we need to make sure we go in, say we were using y1, and we're using x1 and x1. Okay, all you have to do is go to the right of the letter and hit the number 1 on your keyboard. Desmos will automatically use, it'll drop the 1 into the subscript. And then finally, you'll see you get a bit of an error here. Don't panic. All we need to do is change this equal sign into the tilde, the little squiggly line. Okay, that means approximately equal to. All right, so make sure you change your x's to x1, your y's to y1, and your equal sign to your tilde. And then that tells Desmos that you want to use regression. And as you can see, it gives us a really lovely line here in black that does a pretty darn good job of going through or getting as close as it can to all the points that we have from our table. So we get some important information down here. The most important are these parameters, a, b, and c. Those, of course, correspond to our a value, our b value, and our c value that we specified in our initial function. The second most important thing is our r squared value. So if you remember, we talked a little bit about this in class when we were still in class. The r squared value is basically a measure of how good of a job Desmos did in fitting a quadratic curve to this data. If r squared was 1.0, that would mean it's a perfect fit. It perfectly went through every single point with no issue whatsoever. Okay, it's going to be quite rare for us, particularly when we're using quadratics and cubic functions to get a perfect match. In general, you want an r squared value of 0.99 or higher. That means you're getting really, really close, and the function that we've generated is good. It's really good. It's really close. If it's a little less than that, it's fine. Don't worry. It all kind of comes down to exactly what the question's asking you to do. In this case, we've decided we're using a quadratic equation regardless, so we don't have to worry about that. We can go on to the next part. So let's hop back into the notes here. So you can see that the question, instead of using y, it used c for concentration. Instead of using x, it used t for time. That's fine. So just to copy down and to round to 2 decimal places like the question was asking us to do, we had an a value of negative 1.89, which makes sense because the quadratic opens down. We had a b value of 18.76 and a c value of 1.21. So now that means we know the equation of that quadratic that it gave us. We know that the equation would be c equals negative 1.89 t squared plus 18.76 t plus 1.21. All right. Next question. On the calculator, display the graph of the regression equation over the scatter plots and use the graph to answer these questions. So we did that already. Next one. There are domain restrictions on the quadratic function determined from the data in the last section. The minimum value for time is 0. Makes sense. Remember that domain, that means our x values. Okay, that's our time value. The minimum value for time is 0. The maximum value for time is the intercept on the graph where there is no longer any medication left in the blood. Determine the domain for this model. Okay, so we got to go back. We'll take a look here. I'm going to squish this in a little bit just so we can kind of talk about the intercept here. So this quadratic, of course, we have two intercepts. We have one, whoops. Whoa, what's happening? I'm going to stop doing that. We have one, just kidding, I'm going to keep doing it. We have one intercept right here, and we have another intercept over here. But as we know, the last data point that we got from the table was this one. Okay. So as we go down, as we travel down this curve, the concentration of the patient's blood, or the concentration of the medication in the patient's blood is decreasing, obviously because the graph is decreasing. And then once it reaches right here, that's our intercept. That's our x-intercept. There's no longer any more medication in the patient's blood, right? Although the graph continues. It continues down and down and down and down because, well, we know that that's what quadratic functions do. They continue down forever if they open down, and they continue up forever if they open up. But in real life, so what I'm trying to say is here the graph enters the negative values for the y-axis, which in our context is medication. These are negative numbers. It doesn't make sense for somebody to have a negative concentration of medication in their blood. And no, it doesn't make sense, right? Either the medication is in your blood and you have some positive amount of concentration in your blood, or you simply have no medication in your blood, in which case it would be 0, which is represented by our intercept there at 10.16. In this context, in this word problem, you can't have a negative amount. So that's what this question is asking us to do. It's saying, okay, you cannot have a negative amount. So what is the value for x for time when we have 0 concentration in the blood? And in this case, it is after 10.16 hours. Okay, so we'll go back. So we know that the domain for this one is going to be from 0, because where's that 0 going? It's not letting me write here. Apparently it was there for some reason. Okay. In this example, it's going to start from 0, and it's going to go to 10.16 hours. Okay, so if we're going to list the domain properly, it is going to be, actually I shouldn't say it's 0. So here's the thing. Let's talk about that for a minute. Let's go back. Let's take a look right here. This was the actual real life point right here, 0, 0. Because of time 0, there's a 0% concentration in the blood. All right, makes sense. But the model, of course, goes into the negative numbers. It goes to negative 0.0643. So what do we do with that? Because, well, we know that the data starts here. Why would we include this one to the left? Right? So this is just simply a result of regression being imperfect, right? We didn't get an R-squared value of exactly 1.0, right? If we had an R-squared value of 1.0, this line would go exactly through this point, right? So this is what I mean when I say we're simply estimating, okay? For the purpose of this this question, I'm going to say my domain starts at 0, okay? Although technically the line goes back here, I'm going to stick with this one, okay? All right, so yeah, 0 to 10.16. So we're going to say the domain is t such that 0 is less than or equal to t, which is less than or equal to 10.16, and t is an element of the real numbers. Okay, so that would be our domain for that one. Check if I'm still recording. I am. Good. All right. The doctor has decided that the patient needs a second dose of medication when the concentration in the blood is less than 10 milligrams per liter. If the first dose of medication was given at 9 a.m., at what time should the second dose be given? All right, so let's go and take a look here. So the thing with quadratics is it's going to hit 10 at two different spots. Okay, so this is our line for 10 right here. That's 10 milligrams per liter on our y-axis for concentration. It hits it here first on its way up, and then it hits it over here again on its way down. So we're not going to be concerned with giving the patient another dose at this level of 10 because, well, that would just be an insane amount of medication. The graph would spike dramatically. What we're worried about is when the patient's concentration of medication starts to decrease, which is happening over here on this side. Okay, so if the doctor's decided that we need to provide the patient with another dose when there is 10 milligrams per liter remaining, we need to know this exact value over here. On Desmos, you can hold and click and drag and try to get it exactly on 10. It can be a little difficult trying to do that on Desmos. What I would do would be to simply come over here and just type in y equals 10. Oops. Y equals 10. It provides you that line right there. And then you can just come over here and click. And it'll show you where those two lines cross over. All right, so we can see here that there will be 10 milligrams per liter of medication in the patient's blood exactly 9.603 hours after their initial dose. Okay, that's what this point is telling us, because this point here, the 9.603, that's our x coordinate, that's time. All right, so at 9.603 hours since their first dose, which happened at 0, 0, over here, right? Time 0 was their first dose. Their concentration peaks and comes back down and hits 10 milligrams per liter at about 9.603 hours. Okay, so we can come back. So we know that 10 milligrams per liter occurs at at t equals 9.603 hours. So we can convert that extra 0.603 hours into minutes if we want to. All right, so we'll take that 0.603. That's hours. Of course, we have to multiply that by 60 minutes. There's 60 minutes in an hour. And we get approximately 36 minutes. Okay. So, what that means is, oops, not 6. What that means is 9 hours and 36 minutes after first dose is when the second dose needs to occur. First dose was given at 9 a.m. So 9 hours, 36 minutes after 9 a.m. gives us a time of 6:36 p.m. So that is when the second dose needs to occur in order to maintain the medication according to the doctor's orders. Okay, so that's the first question. Let's try the next question. Okay, question 2. A research student was investigating the relationship between job satisfaction, which is given the variable j. It looks like they've placed that on the x-axis here. That's measured by the employee on a scale from 1 to 10, and productivity, which they've put on the y-axis, measured by the employer on a scale of 1 to 100. So it looks like they're interviewing their employees for their job satisfaction and then asking their bosses what their corresponding productivity is. Interesting. Okay, so it looks like they surveyed 12 employees, and we have the results here. And it looks like we're provided a graph as well, a scatter plot. So we got productivity, which is our p-value, our p-value, and we have our job satisfaction, which is j, on the x. Okay. So question A, the student looked at the scatter plot rising from left to right. So here, clearly, we have an increase, right? And suggested that the productivity could be expressed as a linear function of job satisfaction, perform a linear regression on the data, and determine a relationship in the form of P equals A times J plus B, giving A and B again to 2 decimal places. So again here, they're simply using P for Y, and they're using J for X. So really, this is just in Y equals mx plus B form, slope-intercept form. Anyway, doesn't matter. So what we need to do is we need to head over to Desmos, and I'll get rid of this stuff here. And we need to create a new table. And we need to enter that data into our table again. Okay, so I'll do this real quick. So for our values for j, that was our x values. So we did 3, 8, 7, 5, 9, 6, 6 again, 10, that guy really likes his job, 8, 2, 5, and 7. And then the corresponding productivity numbers from the table were 44, 81, 75, 66, 90, 70, 71, 98, 75, 25. That person is not very productive. 68 and 77. All right, and again, I'm going to hit the little zoom function over here so I can see the data properly. Okay, so we have our data plotted there, and as to be expected, that's very similar to the graph that was provided to us in the question. Okay, so the question is asking us to provide a linear regression. So we're going to come in here. We're going to say y1. Well, actually, I'll do it this way. So y equals a times x plus b. All right, so that's the general form of our linear equation. So again, we're not using x and y. We're using x1 and y1. So we have to make sure we come in here, change the y to y1, change the x to x1. And of course, instead of the equal sign, we need to use a tilde to provide for us the linear regression line that we have here. I don't want to use blue because we're already using blue for the points. So perhaps I will just use orange. And that's what we have there. Okay, so we can take a look at our patterns, our parameters. So it looks like we have an A value of 7.91 and a B value of 19.89. And we have an R squared value of 0.9205. So pretty high. I'd like to see it higher. If you remember, usually 0.99 or higher is kind of where you want to be with your R squared value. I guess that it depends on what application you're trying to do, but in general, we want 0.99 or higher. And we don't quite make it there with this one. It makes sense. There's a fair amount of points here that are pretty far away from the line, which is resulting in a smaller r-squared value. But that's fine. The question is just simply asking us to do this to see what we get. So let's hop back to the question. And again, my screen doesn't want to cooperate. All right. So we got an a value of 7.91 and a b value of 19.89. So putting that together, we would get a linear function of productivity being equal to 7.91 times the job satisfaction result plus 19.89, and we had an r-squared value of 0.9205. And I'll come back and we're going to discuss what this r-squared value means in a minute. All right, next question. Another student looked at the scatter plot and suggested that perhaps the relationship could better be represented by a cubic function rather than a linear function with a point of inflection. So if we take a look, that's entirely possible. So although the graph does go up, a point of inflection, of course, so it's going to come up, it's going to curve, and there's our point of inflection right there. Kind of stops, flattens out, and then it continues up again. So that would be a point of inflection. This is not a turning point. So remember, a turning point has to have the graph going from increasing to decreasing. That's not happening here. This graph is very much still increasing the whole time. The curvature just changes slightly. Point of inflection. So this seems reasonable. It seems like we could also fit this data to a cubic function. And that's exactly what the question is asking us to do. So now it's asking us to fit it to this general form right here into Desmos and see what we get instead. So let's do that. Let's go take a look and see what we get. So I can leave this orange line here. We're going to keep it there. What I'm going to do is I'm just going to add another one. Okay. So you should be familiar with the format that you have to enter your data into Desmos now. So I'm just going to do this one real quick. So it's going to be y1 approximately equal to some a value times x1 to the power of 3 plus some number b times x1 to the power of 2 plus c times x1 plus d. And there we go. I'll change this one maybe to a better color, maybe purple, maybe green. Yeah, let's do green. Green's a little better. All right. So if we take a look, it seems like the blue data points are actually a lot closer to the green cubic line rather than the orange linear line. So as you can see, there's a lot of points that are quite far away on the linear line, but on the cubic curve, they're a lot closer. And we can actually, this is where the r-squared value becomes useful. So now we have two separate regressions talking about the same pattern. So as you can see here, our r-squared value for the linear function was 0.9205, whereas the r-squared value for the cubic function is 0.9896. It's higher. So that means that the cubic function fits the data better than the linear function. Okay, so let's go enter these values into our homework here. So we had an a value to 2 decimal places, 0.32. We had a b value, negative 6.37. Our c value of 45.90. And a d value of negative 44.21. So we can fill that in to our function here. So that means we get a p-value equal to 0.32 times j cubed minus, because b is negative, 6.37 j squared plus 45.90 j minus 44.21, because c is negative. Okay, and for this one, we had an r squared value of 0.9896. All right, so this question concludes with a really good question. What model do you think best represents the data? So we talked about that already. That is strictly the purpose of the r squared value, to see how close the data fits to the lines that we have generated. Okay, so what I'm going to say is, because, remember these three dots mean because the r squared value of the cubic function is greater than the r squared value of the linear function, we'll say the cubic function, the cubic function best models the data. Okay. So that means if we're trying to do any sort of prediction or try to see any sort of pattern with the results of this survey, we would want to use the function here in part B, the cubic one. Okay, so hopefully that makes sense. At this point, it would be a good idea for you to start working through the assignment for that one. So that's section 6.3. So in your workbook, that's going to be page 353, questions 1 to 8. I believe that's all of them. Obviously, you're going to be asked to do some regression on the questions there. So for that, you're going to need to use Desmos. If you're comfortable with an alternative program, feel free to use whatever program you want to use. Okay. I know some of us at this time might find it hard to get access to the internet right now. Try your best. We're trying to figure out some solutions for you at the school level. We're not too sure what that looks like yet, but we are trying our best. And take your time. We still don't know exactly what is going to happen as far as testing goes. We're still trying to figure that out. I'll hopefully have some more information for you shortly. But this video was designed mostly to test things, making sure I can get this sort of content up and available for you. There's no expectation at this time for you to finish this assignment right away. Take your time with it. Try your best with it. Hop on the Discord if you have any questions. I'll be sending out a link to that in an email pretty soon. That'll most likely be the easiest way to get a hold of me if you have any questions with the assignment. But for now, that's it. See you next time.